pictures, and gradually we just zero in to the eye implantation. On the view graph, I couldn't find a suitable view graph, therefore I picked a very old talk I gave, and I'm not going to cover the topic of my view graphs. However, the view graph contains many interesting slides, which I would like to show. Dee, could you turn on the PowerPoint?
Sure.
I will also, during my talk, I will trying to touch upon some of my graduate student days, and also give you a feeling about what was the graduate school like 40 or 50 years ago. Well, the title is already misleading, and I talk about eye implantation, past, present, and future. The future is in the area of the material modification of bio research, because this talk was really addressed to the bio topic. So the title was tilted toward the bio. But in today, what we're doing is it's not bio. We may do the bio later on, later years. But however, today, just say we're going to do the implantation. Like you notice, the talk was given in 2009. So now it's almost 12 years ago, but still many of the view graphs still useful. Next, please. Next slides. Thank you. Okay, here I will try to introduce the history and talk about the physics related, and not into detail, but just give you the big picture, tell you the facility, capability, and also during the talk, have some examples and so on. So let's get to the next slides. The next slides, please. Thank you. Okay, this is a very funny wood carving pictures. And this kind of wood carving is really in the old books. Since the invention of the print press, they carved the number, they carved the letter, so they put in the, so this picture is trying to be humor. So actually it's really a correction. It's not correction, it's a cut and paste from a very, very old British book. And the book was about the glass making. But somehow, in this picture here, you'll notice the author was a very interesting. I'm talking about the author is actually is the 20th century author. He's a Mac Thompson. He's an expert in implantation in England. So he took the old wood carving, doctored the left part of the picture, and draw into a source, ambient source, a magnet, and also a target chamber. So almost like back into the 15th century, and people already invent the eye implantation. Of course, this is a joke. So the invention was really the glass. They were trying to use some kind of soil, and also in high temperature, try to make a clay, make bottles, make glasses, and so on. It's a pottery type of industry. So Jim Mayer put this one into his book. The book is Eye Implantation. So sometimes if you want to read more about the implantation, that's an excellent reference book. Next view graph. Okay, 500 years after the view graph, after the previous view graph was 1955. So here, if you look at the date of this patent, US patent, is 1957. So we really talk about 400 years later. And the inventor of this patent is William Shockley. And Bill Shockley at that time was at Bell Lab. And Shockley, Bardeen, and the Cooper, that's a Shockley, Bardeen, Shockley, and Cooper, they just got a Nobel Prize for inventing the semiconductor, because semiconductor is they take a piece of germanium and then they dope it, and then they're making a junction. Therefore, immediately they can really acting like a switch, so a bipolar switch. So since then, Shockley was thinking about doping was done by diffusion. But how about implantation? He was thinking about using an accelerator, bombarding the germanium into the bombarding the germanium with boron or with arsenic to form a junction, and then use that junction. Therefore, he had this idea. He said implantation could be a way to do doping the semiconductor. So in 1957, he filed this patent. So this is the first idea about using implantation to make semiconductor. So digress the story is so Shockley at that time went to California, because in Berkeley they have implantation. They don't. They have an accelerator for nuclear physics. So he feel there may be something to do with it. So he set up the Fairchild. No, he set up the company then called the Fairchild Semiconductor. Later on, they become the Fairchild Camera, become a camera company. The camera company have a group of people not very happy with him, because he wants to do implantation while the other group want to do semiconductor, making devices and so on. So this group of people spin off. There were 12 people involved in his company. They just departed. So eventually the Shockley Semiconductor Company died. But this group of people, they start a company. The name of the company is called Intel. It's called Intel. No. Could you put my face into the camera?
I cannot, because you need to adjust the angle of your iPad.
Okay. Well, what I'm saying is sometimes I want to almost like doing demonstration and so on. So
We can see your hands, and
you,
we
you
cannot.
can see
Yeah.
see my hand, right?
Yes.
You can see my face.
Half.
Okay, one thing is I don't need to see the view graph, because my big camera, no, my big screen on the side, I can see all the view graph.
Mm-hmm.
So I'm talking about this. Oh, I know what you're talking about. It's so the student can read the view graph, but they cannot see me.
We
can even
you.
see you. We can see you, and we can also see the presentation.
All
Both.
right,
We can see both.
Okay, then that's good. That's good. So in that case, I will continue my talk. So I was talking about this group of 12 people become the Intel Corporation. They formed the Intel. When they formed the Intel, that's already 20 years later. Okay, 1957 is the patent. 1970 or 72, the Intel started. So at that time, to give you a little bit of a historical story, is 1974, I finished my postdoc job at Caltech. So I was looking for jobs. So then one of my high school classmates back in Taiwan, he is one of the 12 people which are funding the Intel. So he called me from from Northern California. Today is the Silicon Valley. So the Silicon Valley actually started because the William Shockley is the grandfather. And the industry is the first industry is the Fairchild semiconductor, then Fairchild camera, then Intel, then gradually the chronology really start. The Intel was spin up into company, until today, we had one of the most important industry in the world, just in Silicon Valley. So in '74, so my classmate called me. He said, "Well, why don't you join this new company, Intel?" And so we are really looking for making semiconductor device. And I said, great, because I learned eye implantation from Jim Mayer. I said, this is a great way to do it. I also say, well, your company's grandfather company is Shockley, also have a patent about implantation. So why don't you people do implantation? Then I know how to do it. So let me come to your company, give a talk. So I went to Intel. Today I can boast. I can really talk about, well, I gave a talk in Intel in 1974. And 75% of the Intel employee came to my talk. So people will say, well, you must be joking, and the Intel is a big company. How could so many people come? Actually, only 12 people came to my talk, but that's the whole company. So I gave an excellent talk. Of course, I still need to find out my geograph for that talk. But anyway, the talk was talking about taking silicon, bombarded with boron, then we get a p-type material, bombarded with arsenic, we get an n-type material. We bombarded with both, we get a p-n junction. How do we anneal them? And how do we start making device? A single device, multiple device, how about the integration of the devices and so on? For the story, to complete a historical story, is at the end of my talk, so one engineer stood up. He said, Dr. Chu, you gave an excellent talk. However, to be honest with you, I think the eye implantation in semiconductor will never make it in our lifetime. So he made a very strong statement. And then, of course, I was kind of disappointed. I feel I gave a good talk. I cannot convince the company. So at the end of the interview, my high school classmate, his name is Albert Yu. Albert Yu later on turned out to be the vice chairman of Intel. So he died a few years ago. So he put me into the corner. So told me, say, we can, and it looks very bad. And out of 12 people, you only get one positive vote. All the 11 votes is a negative. So naturally, my interview was, I flunked the interview. I did not go to the interview. So I just went back to Caltech. So that was the story. And so then later on, many years later, and in the conference, I bumped into my high school classmates, and by then the implantation was well accepted. It became the most important part of the process in making semiconducting device. So I told my friend, I said, well, in the old days you didn't hire me. Then 4 years later, you hire somebody else to do the implantation. And then also digress a little bit. After I flunked the interview, so I gave the same talk at IBM. And IBM listened to my implantation talk. He said, well, we like the idea. So they hired me. So I went to IBM in 1974. spent 6 years there doing the implantation, help them to build the device, build the bipolar device, and integrate the device. Of course, that integration is still pretty large scale type of implantation. So the interesting part is the Intel was 4 years behind IBM. So they were 4 years behind. And then, however, they start catching up because they have very good design, circuit design, and so on. And also later on, some of my students went to Intel, into my Intel. So one of my students, when I was teaching at Chapel Hill, North Carolina, one of my students by the name of Shandu, last name is Shandu. So Shandu, getting PhD and start looking for job. So he applied IBM, Intel, and also Micron Electronics and several small companies. So the Micron accepted him. So I guess Micron Technology, so in Idaho. So they gave him an offer. So Shandu came to me. He said, well, Dr. Chu, and I need your advice. Where should I go? Should I wait for IBM, wait for Intel, or should I just go to Micron? So I told him, I said, go to Micron. And even Intel gave you an offer, even IBM give you an offer. And he said, why? And nobody heard about Micron. They only, we all know Intel by then. We all know IBM, big company, good company. I told him, I say, Shandu, you are a very talented individual. If you go to IBM, you were one out of the 20,000 people, and nobody will really listen to you. They'll ignore you, and so your talent will not shine. But if you go to a small company like a Micron, people recognize your talent. You can really do very well. And the same thing with Intel. Okay, they are pretty much follow their own plan, and so they are not going to listen to a newcomer, a youngcomer. So he went to Micron, and so interesting enough, and at that time I had a patent. Then he wants to get into the patent, so I told him, I say, if you are not involved, you are not involved, and then invent your own stuff later, so you become an inventor. He went to Micron. He invent one after another, after another, after another. He has so many patents. If you get on the web, you can look on the top 10 top inventors of the world. So there were 10 names. So the names really start from in the old days, they start from the Alexander Bell, from the Thomas Edison, and so on. Because life or whether they are alive or whether they're dead, they list the number of patents they have and come up with the name of 10. So by the time I'm talking about almost like 10 years ago, Shandu became the top number 4 inventor of the world. Okay, while Thomas Edison was number 5. Thomas Edison used to be number 4. So I'm talking about I want to use this one, trying to talk about graduate student, which company to go. And it turned out I made the right advice to Shandu. He went to Micron Technology and become a vice president there. And he in charge of a whole research lab. And I remember in one year, this is 6 or 7 years ago, he had 400 patents in 1 year. So I told him, I said, what? 400? How could that be? Yeah, I only have 28 in my lifetime, and you have 400 in 1 year. So this is impossible. So just imagine if you want to sign 400 documents, and so this almost you sign several per week. On that. So I said, well, I cannot even read that many patents. So how could you? He said, well, this is pretty easy. my first few patents made lots of money because people have to pay trying to use your patent licensing. Then I used the money, hire a team of lawyers, hire a team of engineers. Of course, he didn't hire, the company hired. And therefore, all he has to do is go to the, every morning he will go to the lecture room, and he said, "Well, here's my idea." He start right on the blackboard or on the whiteboard. Then he tell his engineering group, he said, "Work out the detail." He tell his lawyer group and write it up. So all he has to do is sit there thinking and using a pencil, and all the rest of them doing the chart making and so on. So this is why he become very, very productive. And also the patents almost like rabbits. If you have two of them together, then pretty soon you have 1,000 of them. So I mentioned Shandu's name. It's a Shandu in I guess 2018, 3 years ago, he won the prize. This prize is called the Andy. Okay. The prize was named after the Intel's founder, Intel's chairman, Andy Grove Award. So in the semiconductor industry, Andy Grove Award almost like a Nobel Prize award. So that means my student went to Micron. Interesting enough, he did not go to Intel because I asked him not to go. Then so many years later, he got the Intel prize, the top prize of that. And then the one who offered him the prize, Andy Grove, was the engineer, stood up on the table, said, "Dr. Chu, and eye implantation will never make it in my lifetime." So that's sort of close the story about my involvement and trying to be one of the early advocates on implantation, but being denied, and by Andy Grove. Andy Grove was a following William Shockley. Also, he is a follower. He's a spin-off from that. And also, Andy Grove comes from Hungary. The Hungarian Revolution, during that time, some of the high school students walking on the street, trying to start revolution toward the Hungarian government. So when the Hungarian government has no way trying to really suppress them, then they invite the Russian army, the tanks, the Russians, and came to Budapest and try to. Then many students escaped. So one of the people escaped is Andy Grove. So he came to California and educated there, and also become the Intel chairman. Then his classmate stayed in Hungary and become the academy, also working on implantation, turned out to be my friend later on. So his name is Joseph July. He and I corresponding. And also, just 3 years ago, he went to one of the fest shop, which celebrate my awarding. He was awarded for that, and so he came to Galveston, and D. Chen met him. So he just died a few months ago. He was the classmate of the Andy Groves. So I would say the life of two Hungarian students, okay, one become the Intel chairperson, one become the academy, chairman of the academy in Hungary, and they both died a couple of years ago. Let me get to the next view graph. Okay, now this is the view graph. I want to get you the big picture. The implantation really involving a target and a particle. The particle hits the target and stay inside. They will call implantation. If it getting out, it could either backscatter or penetrate, go through transmission. Okay, so the implantation here, at least all the parameters. So what are the parameters we're going to be involved? For example, in this view graph, first is the beam. Well, we want to find out ion implantation. What is the ion? What kind of ion are we talking about? So the thing is nearly all elements in isotope can be used. And also sometimes a dimer can be used. So the largest implantation I have involved is carbon-60. You use a buckyball. You use a buckyball, you strip an electron or you add an electron to it. Once they charge, then you can manipulate them by setting up the voltage. Therefore, they will fly. They will fly. So the implantation really based on your imagination. So I remember some of my friends, they actually trying to implant dust particle. They use dust particle involving thousands of atoms, and they can implant and so on. So the beam is based on your imagination. But for semiconductor, we're mostly using dopants like boron, arsenic, phosphor. And sometimes people using oxygen to implant forming oxide, nitrogen implantation forming nitride, or the implantation can allow you to forming doping, forming alloys, forming compounds. And so depends on your imagination. Energy. One can do KeV to MeV to GeV, depends on the application. And also because the accelerator, you can do in the KeV, MeV, or GeV. Actually, if you hook up a battery, you can have a 10 EV, okay? 10 electron volts type of thing. Of course, 10 electron volts particle has no penetration power. They probably only stay at the surface and then disappear and so on. Actually, in semiconductor, the higher the energy, not semiconductor, any material, the higher the energy, the deeper it goes. Therefore, the KeV implantation turned out to be important because you want to make the dopant very, very shallow. Once you start making device, the miniature of the device getting smaller, smaller, smaller. When you're smaller in the area, you also want to smaller in the depths. Therefore, you make a three-dimensional, very, very tiny, tiny device. So the KeV implantation is as important as the MeV and so on. Most of the production, like your computer, your cell phone, and so on, the implantation are nearly in the 100 keV region. 100 keV region. Our implanter could do up to 60 keV, or then from the ion source. Then after the ion source, we can do 100 keV, 500 keV, up to 10 MeV by multiple charge. Therefore, the energy is also a parameter which you can control. Depends on your design of the experiment and also design on your application and the physics you want to study. Depths. Depends on energy. They can go in very shallow, nanometer and to micron or to centimeter, depends on what's the energy we're talking about and so on. On the left-hand side of this view graph, we're talking about what are the parameters: the beam energy, the depth, the dose. Dose is really the concentration. The higher the dose, the more you can put into it. Start from parts per million to a few percent, or to an alloy concentration, or to a compound, and so on. So it really depends on the amount. Area, by masking or by photolithography, and one can really implant very tiny area or very large area, or a large area with many small windows open. So it depends on the need, depends on the application. Now we talk about beam implantation. Implantation to what? Okay, that's the target. Okay, on the target part, semiconductor is the one we studied very earlier. Metal is very important.
Well, Dr. Chu, I have a question.
Yes.
Yeah, you've talked about the area. So I'm wondering, is it possible to, for example, implant a given number of ions precisely, maybe 10 ions precisely?
Okay, the first is thinking about the area is like the window on your ceiling. You open this window, then the sunbeam will shine into the room.
Mhm.
So the window could be as small as a few nanometer. It could be as big as few micron, or could be as big as a few centimeter, depends on your application. But in microelectronics, you want to make a million device within a square centimeter. So that means you're going to have a million windows. You do the implantation. Then you use the second mask and have another million windows, which overlap slightly. Therefore, you can make junctions. Therefore, the window, design of the window, where is the window, the size of the window, and the repetition of the window is start making multiple devices.
Okay.
Did I answer your question?
Yes, but the last thing is that have you, okay, is it possible to implant just maybe 5 or 10 ions precisely? Is there a method for that? Do we have to use the photolithography? I don't know about the photolithography. Is it a method to restrict the number of ions that are going into a sample precisely?
Okay, let me, very good question. So let me digress into a different area.
Okay.
So this area is, for example, I want to make an anti-dopant. In order to make an anti-dopant, I need a phosphor implantation. Okay, so when I do the phosphor implantation, the beam current is on, the phosphor goes through a window. This window is pretty large. Let's just say a micron by micron window. And therefore the phosphor distribution in this window is first we say it's a pretty uniform, but still there could be some area have more phosphor, some area have less phosphor. The distribution is a Poisson distribution. So your question reached to a point is a very clever question phrased by one of the Japanese many years ago. He said, can I very cleverly having a window. This window is very, very tiny, very tiny. And also, if I can implant only single phosphor, one phosphor into this window. Okay, he was phrasing that. Lots of people was laughing. Okay, who needs that? And the stupid question and so on. But he did it. He did it. So what he did is he has a mask with a very small, tiny hole. Then he is sending the phosphor beam go through this hole, but the beam is so weak, very, very weak. Therefore, the phosphor doesn't flow like a water faucet. You turn it on, it just zoom. No, it become a drip almost like a atom by atom type. Okay. Atom by atom. Then he was saying, if you only want to implant a single atom, then that means if the single atom passing through the hole, touching the substrate, then he have to immediately shut off the beam by using a blank shutter. And therefore, on the other side, once the beam goes through it, this message, there's going to be electron cloud around. So once he sees the electron cloud, a automatic switch off the beam.
Okay.
Now he accomplished a single atom implantation. Okay.
Understood.
Okay, then he using the single atom, trying to really making a device. Of course, it's a very slow process. He will implant the phosphor uniformly, not like a random distribution, Poisson distribution, uniformly on the device. And then he will compare this uniformly distribution, almost like a checkerboard. You put a piece by piece all on the square. But the other one is you throwing them all in random into the square. He compared the performance of these two devices. He found out the timing on the device for a well-designed single implantation uniform distribution device. The clocking is very, very sharp, while the other part is a clocking, is a Gaussian clock. Okay, it has a well-defined frequency, but also it has a window, it has a frequency range. So this is talking about is I appreciate the question because it's although people may think it's a stupid question, but on the other hand, it's how as an engineer you can look at those parameters, thinking about can I really stretch or twist the device, twist the parameter and trying to fit the need I want. People will say, why do you want to need that? And maybe you never. But on the other hand, it's that your need may perform certain kind of function where other device cannot. All right.
Yes.
So back to the target. The most important in the application chronologically is semiconductor. Like we've witnessed 1955, the semiconductor patent, although the patent was sitting there almost for 20 years. And then until Jim Mayer and a few people at Bell Lab start using implantation to make device. I was very fortunate trying to be in Jim Mayer's group and also get our group get into the many good publications and also have many good devices, such that I become one of the interviewer, went to Intel. Although Intel didn't believe it, but 4 years later, they changed their mind. And then even today, their implantation, if you look at the business news, is their implantation have difficulty. They cannot reach into 7 nanometer line width for the gate. And therefore the other company were better than Intel. So the Intel stock drops almost by 40% just due to this particular news. Okay, now they're still struggling and because of the implantation part. I was talking about my classmate, Albert Yu, and he is the one developed the 365. There's a chip called 365 Intel. Then there's another one, 335. Let's see. 375. Then the next chip was 475. Then by the time they're going to call 575, they say that's too clumsy. They change that to Pentium. Pentium, everybody knows Pentium. The Intel Inside, if you open your PC, there's a Pentium, there's an Intel Inside in your computer, so that's the Pentium device. This is developed by my classmate. He lead his team and gradually designed the 375, 475, then Pentium, and become the vice chairman of Intel. So because of high school reunion, so I see him a few times over the years. Once I met him, I said, well, and I said, do you remember the interview? He said, of course I do, and you didn't get a job. I told him, I said, well, and so it's I feel sorry I cannot convince you people to do implantation 4 years earlier. And nevertheless, you are very strong. Your team catching up, even you're 4 years behind IBM. Then I said, well, and after IBM, I went to become professor at Chapel Hill, UNC Chapel Hill, then University of Houston. I said, well, you and I, we totally have different paths. If during the interview, so if I convince your people, I probably your teammate and probably working for you. Then he told me, he said, Wickham, you're lucky you didn't come to Intel. I said, what do you mean? I'm lucky. If I'm in Intel, I probably would be millionaire, multi-millionaire. He said, no, there are lots of things money cannot buy. Look at yourself. You have a good family. You have a good family, a good life. You have good students. Look at me. And I worked till very, very late in the evening, drove home, and then pick up my baby girl and my baby daughter and kiss her and put her down. And by 6 o'clock, the alarm clock rang. I had to really rush to the company. And with traffic in the Silicon Valley very bad, and you don't have this kind of headache. It's money doesn't mean anything. The life is the lifestyle. So this is really the side story. Okay, we're talking about different life. So the last line of this slides, energy loss, DEDX, range, ionization, damage, is all the very, very important physics phenomenon. So it is the understanding about the last line, those 4 items, which really build up the whole industry. For the industry for semiconductor, the industry for metal, alloy formation, the ionization, and also the radiation damage. The damage, the last item, is precisely what Professor D. Chen is doing now. But in doing so, he has to worry about the implantation. How deep do they go? What is the energy loss? So it's the ionization process, is the damage anneal, and also the temperature also get involved. So in the intermingle of those several items on the bottom line, it's several thousands of people working on it. Also the industry, the government, and the whole community is worried about that. Okay, although they are very, very simple items, very easy to look. And also the definition may take you 5 minutes to understand, but the detailed physics is quite long. I studied DEDX, the first item. I would say it took me about 4 years. 4 years. Of course, right now, it will be much faster for all the other students. You probably can do it in 4 days. Because in the old days, you had to really do everything, which they don't exist. You have to invent the concept. You really have to do it. The few paper you can read is a Niels Bohr paper, Lindhaus paper. Although there were also hundreds of papers follow that, but still it's so young. The field is so new, and therefore one has to do it. For the 3-item DDX ranging ionization is very clean, very simple physics concept. And I feel every student, by reading it, you can master that in probably 2 weeks. The damage there's a complexity. What D. Chen is doing on the damage is even more complex, with high radiation, with high temperature, and those complications that could involve many people working for a few years to solving the problem for the industry. But yet the simple physics part are still there. So I strongly encourage students trying to really gradually get into it. First is trying to get into DEDX, and then also enter the understanding. So let me get to the next view graph. Next one. Okay, the important part on the DEDX unconceptualized is the energy loss. The energy loss containing 2 components. One is electronic, one is nuclear energy loss. going to electronic energy loss. So first is the atom is made of nuclei with electron cloud or orbital electron around it. So let's talk about the size of nuclei. The size of nuclei is femtometer. Okay, femtometer is tiny, tiny, tiny ball. Let's say this is a nuclei, a femtometer. My mouse is a femtometer. Okay, the electron around it occupy its fraction of a nanometer. Okay. So we're really talking about we really talking about a very tiny nucleus surrounding with large volume of electrons. 10 to the minus 15 is for the nuclei, or 10 to the minus 9, or 10 to the minus 8 is for the atom, 10 to the minus 8. So there was some order of magnitude difference. So now imagine, so if you have a material, let's take this book. So here's my material. So if you look this material into a microscope or nanoscope type of looking here, you will only see the nucleus, only see the nucleus. Now the electron here is invisible, permeated all around it. And also the volume of this one is mostly electrons, while the location is electrons everywhere, while the nucleus is only occupied with the separation, nanometer separation. So now we talk about DDX. Now we have ion beam coming into it, ion beam into it. This ion beam is positive. Okay, let's say alpha particle, proton, or carbon, or implantation is boron or arsenic. It could be positive, it could be negative. Even it's negative, once they enter into the material, the electron start missing, so they become positive. They become positive. So this positive is material enter into this target. Just imagine yourself. Suppose you are an astronaut. You are really having a spaceship. So now you are alpha. You call yourself alpha. You're alpha particle. You spaceship. You go into the outer space, and the outer space has lots of rocks. Really sitting there. You say, "Hey, if I hit a rock, I'm dead. I'm dead." But the point is, the rock is very, very, very separated, hugely separated. The chances for you to hit a rock is very, very little, very little. So therefore, you really just blindsided. You just go straight and so on. So if you are unlucky, and very, very unlucky, maybe 1 out of a million, and you hit a rock. But most likely, you're just traveling in the vacuum. So what are you touching? You're touching the electrons. Although those electrons are orbital electrons, but to you, it really doesn't matter. They are negative particles. Therefore, do they slow you down? Yes, they do, because the positive ion is positive charge, electron is electron. So there's a Coulomb interaction. So when you are traveling, so also you have some electron going to be gathered behind you and almost try to follow you. So you are traveling very fast. So this Coulomb interaction slow you down. This type of slowing, the electronic energy loss, almost like a friction. Like you shooting a gun bullet. You're shooting a bullet. You fire a bullet into the air. So the air gives you resistance. Therefore, your bullet slow down until you stop. Once you stop, that's called range. Okay, that's how deep you go. You're into the material. So therefore, I'm showing these two terms, electronic energy loss and nuclear energy loss is these two terms. So I emphasize on the electronic energy loss. So this is the most important part. The nuclear energy loss, and I didn't emphasize them because they are very rare occasions because you just collect them. But with one exception, a very low energy. If you have very low energy, and then what happened is the nuclear collision turned out to be nuclear energy loss, turned out to be a large number. So I think I'm already reaching 1 hour. So first is I will stop talking here. Then the second thing is I will send you the energy loss chapter, so you can read the energy loss chapter. Then the next time when we meet, we discuss energy loss. So also the view graph, you can obtain from D Chen because this 24 meg, very large view graph size. So you can copy from him using a stick memory stick. So let me just stop here. So next time I will pick up from here. Any question first?
Not really a question, but just a, kind of like, thank you so much for doing this lecture for us, because it gives us a better picture and understanding to what we were working on or what we were reading. It kind of like fills in the gaps and connects the dots that we weren't able to see. So
Okay.
Thank you so much for the history and kind of like showing us the direction to where everything is going, and maybe giving us a glimpse at what to work on in the future. Thanks.
Good. I try to, in the first couple of lectures, I try to emphasize on the big picture, not get into the detail. So the once you get into the detail, all the mathematics and so on, I feel it's tiring and also it's boring. And I leave them as reading material. So I want you to read the detail. When you read the detail, if you don't understand, you bring the question up. Then I can really get into the what are the relevancy and so on, why it's important and so on. Good.
Yeah, thank you, Dr. Chu, for this lecture. As Dennis has said, they are really very good for us
Okay.
They're really very important because, for example, for me, when I was writing an email to request for these lectures, I'd read several papers and I wasn't understanding, but and so I look forward to the detail, more detailed lectures. I hope that it can be put into program maybe every Tuesday, if you can, so that until when you exhaust all that you want to teach us.
All right.
I really appreciate that.
So let's just do it every Tuesday. That would be okay.
By the way, every Tuesday a little bit challenge because when I'm not sure if we can just get everyone together every Tuesday. But let's try that. Let's just schedule Dr. Chu's lecture every Tuesday, and if something change, and we can just reschedule it.
What about for Thursday? Because I remember that Tuesday always has colloquia in the same time. What about Thursday?
I think Tuesday is fine. Tuesday is fine, and we can just discuss the after Dr. Chu's lecture. We can just update some information. I think I'm okay with that. I don't know if everyone else have the same time, have the no time conflict. But if you think that's a good time for you, and you have attended the meeting, we can just schedule every Tuesday for Dr. Chu's talk, unless there is further notice.
What he was saying is on Tuesday, physics department also have a colloquium talk.
Oh, at 2.
At 2. So you have time conflict, right?
Yes.
Let's move to the Thursday, every Thursday, 2 p.m. and our routine group meeting time. What do you think?
I agree with that.
Okay.
That'll be okay.
Anyone else has time conflict? Okay, if
That's
no, if no
Yeah.
time, yes,
I have lab during that time.
you have wondering what?
I have a lab during 2 p.m. on Thursdays.
2 p.m. Thursdays, and how long for that?
It's usually from 1 to 3, but sometimes it gets off early, so I might be able to come by 2.
Yeah, each time, and I'm going to record the video, and you can just review the video if you missed the lecture.
Okay, thank you.
Thank you.
One last question, Dr. Chu.
Yes.
Yeah, about the range. When ions are being implanted onto a sample, do they have different ranges, or it is possible to have the same range for all the ions that are being implanted into the sample? Like, how's that really measured?